world has witnessed many revolutions, each transforming society in profound ways. We've seen the agricultural revolution, which changed how we grow food, the industrial revolution, which reshaped manufacturing, and the information age, which revolutionized how we process and share information. But one of the most profound revolutions of our time is happening quietly, behind the screens of our devices. The software revolution, which is transforming every aspect of our lives. Software engineering is the invisible hand that shapes our digital world, driving innovation and efficiency. It's the art and science of designing, building, and maintaining the software that powers everything from our smartphones to our cars, from the apps we use daily to the systems that run our cities. From medical devices to financial systems, software is integral to modern life. Without software, our world would grind to a halt, leaving us disconnected and disorganized. This essay takes us on a journey through the history of software engineering, exploring its roots and evolution. We'll explore its humble beginnings, its growing pains, and the milestones that have defined its progress, and its remarkable evolution into the complex and ever-changing field it is today, constantly adapting to new challenges and opportunities. Join me as we trace the footsteps of the pioneers who dared to imagine a world transformed by software, and who laid the groundwork for the digital age, and discover how their innovations have shaped the digital landscape we inhabit today, influencing every facet of our daily lives. The seeds of software engineering were sown long before the first computer was built. The journey began with mechanical devices designed to aid in calculations, laying the groundwork for future innovations. In the 19th century, Ada Lovelace, an English mathematician, recognized the potential of Charles Babbage's analytical engine, a mechanical general-purpose computer, to go beyond simple calculations. She envisioned a machine that could manipulate symbols and process information in ways never before imagined. She wrote what is considered the first computer program, a set of instructions for the analytical engine to compute Bernoulli numbers. This was a groundbreaking moment, as it demonstrated the concept of a machine following a sequence of operations to achieve a result. Fast forward to the mid-20th century, the invention of the electronic computer marked a turning point in history. These new machines were capable of performing complex calculations at unprecedented speeds. These early computers, massive machines that occupied entire rooms, were primarily used for scientific and military purposes. They represented a significant leap forward in technology, but they were also incredibly cumbersome and difficult to operate. Programming these early computers was a laborious task. It required meticulous attention to detail and a deep understanding of the machine's architecture. Programmers used punch cards or paper tape to input instructions, and debugging was a nightmare. Each error meant starting over, often leading to long hours of painstaking work. As computers became more powerful and their applications more diverse, the need for a more systematic approach to software development became clear. This evolution paved the way for the formalization of software engineering as a discipline. The stage was set for the birth of software engineering, a field that would revolutionize how we interact with machines and process information. The 1960s witnessed a surge in the demand for software. Computers were becoming smaller, faster, and more affordable, leading to their adoption in various sectors. This rapid growth, however, led to what became known as the software crisis. Projects were often delivered late, over budget, and with numerous defects. Software was difficult to maintain, and the process of developing it seemed ad hoc and unpredictable. It became evident that simply writing code was not enough. A more disciplined and engineering-oriented approach was needed. In 1968, a NATO conference coined the term software engineering to address this crisis. This marked a turning point, signifying the recognition of software development as a distinct engineering discipline. The search began for better methods, tools, and techniques to manage the growing complexity of software systems. One of the key responses to the software crisis was the emergence of structured programming in the late 1960s and early 1970s. This period marked a significant turning point in the history of software development. Pioneered by Edsger W. Dijkstra, structured programming emphasized the use of structured control flow constructs, such as loops and conditional statements, to improve the clarity and maintainability of code. Dijkstra's work laid the foundation for modern programming practices. Before structured programming, programs were often written as a series of Goto statements that could jump around the code in a haphazard way, making them difficult to understand and debug. This chaotic approach led to numerous errors and inefficiencies. Structured programming brought order to this chaos by encouraging programmers to think in terms of well-defined blocks of code that performed specific tasks. This methodical approach made it easier to read, write, and maintain software. This shift in programming paradigm led to a significant improvement in the quality and reliability of software. Teams could now work more efficiently, reducing the time and cost associated with software development. It also paved the way for the development of higher-level programming languages that made software development more accessible. These languages further abstracted the complexity, allowing developers to focus on solving problems rather than managing intricate details of the code. Section 5. Object-Oriented Programming, a New Perspective. The 1980s witnessed another major paradigm shift in software engineering with the rise of Object-Oriented Programming, or OOP. OOP introduced a new way of thinking about software design, focusing on objects, which are self-contained units of data and the methods that operate on them. Popularized by languages like Smalltalk and later C++, OOP offered several advantages over traditional procedural programming. It promoted code reusability, modularity, and data encapsulation, making it easier to develop and maintain large, complex software systems. OOP became the dominant programming paradigm in the 1990s and continues to be widely used today. It has profoundly impacted software engineering, leading to the development of numerous design patterns, frameworks, and tools that have shaped the way we build software today. Section 6. The Agile Revolution, Embracing Change. The late 1990s and early 2000s saw a growing dissatisfaction with traditional, plan-driven software development methodologies. These methodologies, often referred to as waterfall models, were seen as too rigid and bureaucratic, struggling to adapt to changing requirements and the rapid pace of technological advancements. In response to these limitations, a group of software developers met in 2001 and drafted the Agile Manifesto. The manifesto outlined a new set of values and principles for software development, emphasizing collaboration, flexibility, and a focus on delivering working software incrementally. Agile methodologies, such as Scrum and Extreme Programming, gained widespread adoption, revolutionizing the way software teams work. Agile emphasizes iterative development, frequent customer feedback, and the ability to adapt to changing requirements, making it well-suited for today's fast-paced software development environment. Section 7. The Software Landscape Today, a World of Complexity. Today, software engineering is a vast and ever-evolving field. The software we build is more complex than ever before, and the pace of innovation shows no signs of slowing down. We live in a world of interconnected devices, cloud computing, big data, artificial intelligence, and the Internet of Things. Software is no longer just about writing code. It's about understanding complex systems, designing for scalability and security, and constantly adapting to new technologies and user expectations. Modern software development requires a diverse set of skills, from traditional programming languages to cloud platforms, DevOps practices, and user experience design. The challenges are immense, but so are the opportunities. Section 8. Challenges on the Horizon, Navigating the Future of Software. As software continues to permeate every aspect of our lives, software engineers face a number of challenges. The increasing complexity of software systems demands new approaches to design, development, and maintenance. Security is paramount. As our reliance on software grows, so does the potential impact of software vulnerabilities. Engineers must prioritize security at every stage of the development process to protect sensitive data and critical infrastructure. Ethical considerations are also coming to the fore. Algorithms are making decisions that affect our lives in profound ways, from loan approvals to job applications. Ensuring that these algorithms are fair, unbiased, and transparent is crucial. The future of software engineering will be shaped by our ability to address these challenges and to harness the power of emerging technologies responsibly. Section 9. Conclusion. The ever-evolving world of software. From the early days of punch cards to the age of artificial intelligence, the journey of software engineering has been marked by innovation, adaptation, and a constant quest for better ways to build software. What began as a response to the software crisis has evolved into a vibrant and essential discipline that underpins our digital world. As we look to the future, one thing is certain: the world of software will continue to evolve at an unprecedented pace. New challenges will emerge, and new solutions will be found. The software engineers of tomorrow will need to be adaptable, creative, and ethically minded to navigate this exciting and ever-changing landscape. The future of software is unwritten, and it's up to us to shape it.